in the first place? Well, all those bumps and folds in the ear have a meaning, evolutionarily speaking. Based on what direction the sound is coming from, sound waves bounce around inside the ear, there's some constructive and destructive interference, and the result is a change in volume. The phase of the sound also shifts, depending on what path the sound wave took to reach the ear canal. These volume changes and phase shifts are different for each direction and also vary depending on the frequency of the sound. Head size and head shape also impact the sound in a similar fashion. The way that the sound changes, based on direction and frequency, can be encoded in a table called the Head-Related Transfer Function, or HRTF. Here's part of one. The vertical axis is the frequency, the horizontal axis is the direction, front, back, left, right, and the color gives the degree of attenuation of the sound at that frequency. The HRTF is as unique to an individual as a fingerprint is. In fact, you're looking at mine right now. Here's how we measure an HRTF. We've taken hundreds of people through this process. We put a microphone in the subject's left and right ear canals, and then sit the subject down in the middle of an array of 22 speakers. We then play an audio sweep from each speaker as we rotate the subject. In the course of 10 or 20 minutes, we're able to sample the HRTF at over 1,000 locations. Using an HRTF when rendering audio creates unparalleled quality, but it's computationally expensive. The simplest way to use an HRTF is to process a sound source to make it appear as if it's coming from one of those 1,000 locations we sample. Unfortunately, the processing has to be done in frequency domain rather than time domain, so there's multiple fast Fourier transforms needed for every sound source for every audio tick. That's a lot of multiplies. This computational complexity was the determining factor for our strategy. It meant we had to bite the bullet and design and build a custom hardware unit for 3D audio. Collectively, we're referring to the hardware unit and proprietary algorithms we run on it as Tempest 3D Audio. The meaning of 3D audio and technology should be pretty obvious here. As for Tempest, I feel it really reflects our goals with audio. It suggests a certain intensity of experience and also hints at your presence within it. We're calling the hardware unit that we built the Tempest Engine. It's based on AMD's GPU technology. We modified a compute unit in such a way as to make it very close to the SPUs in PlayStation 3. Remember when I said that they were ideal for audio? So the Tempest Engine has no caches, just like an SPU. All data access is via DMA, just like an SPU. Our target was that it would have more power than a CPU, thanks to the parallelism that a GPU can achieve, and that it would be more efficient than our GPU, thanks to the SPU-like architecture. The goal being to make possible near 100% utilization of the CU's vector units. Where we ended up is a unit with roughly the same SIMD power and bandwidth as all 8 Jaguar cores in the PlayStation 4 combined. If we were to use the same algorithms as PSVR, that's enough for something like 5,000 sound sources. But of course, we want to use more complex algorithms, and we don't need anything like that number of sounds. It would have been wonderful if a simpler strategy, such as using Dolby Atmos peripherals, could have achieved our goals, but we wanted 3D audio for all, not just those with licensed soundbars or the like. Also, we wanted many hundreds of sound sources, not just the 32 that Atmos supports. And finally, we wanted to be able to throw an overwhelming amount of processing power at the problem, and it wasn't clear what any peripheral might have inside of it. In fact, with the Tempest Engine, we've even got enough power that we can allocate some to the games, to the extent that games want to make use of convolution reverb and other algorithms that are either computationally expensive or need high bandwidth. But the primary purpose of the Tempest Engine remains 3D audio. Now, 3D audio is a major academic research topic. It's safe to say that no one in the world has all of the answers. And the set of algorithms that has to be invented, tuned, or implemented to realize our vision for 3D audio is immense. For example, use of HRTFs in games is quite complex. Before, I talked about making a sound source appear as if it's coming from one of those 1,000 HRTF sample locations. But for high-quality 3D game audio, we have to handle other possibilities. The sound source might not be at one of the 1,000 HRTF sample locations, so we have to blend the HRTF data from the closest locations that we have sampled. The sound source might be moving, which needs very special handling as that blend keeps changing, and that can cause phase artifacts in the resulting audio. Or the sound source might have a size to it, meaning it should feel as if it's coming from an area rather than a single point. There's also whole categories of approaches to be handled. 3D audio can be implemented using individual processing of 3D sound sources. But alternatively, ambisonics can be used for 3D audio. Ambisonics being somewhat like the spherical harmonics used in computer graphics. And finally, there's audio devices. The player might be using headphones or TV speakers, or have a higher-end surround sound setup with 6 or more speakers, all of which need different approaches. That's a lot of